So now I'm going to start my presentation. I'm Junjun Li from Nanjing University of Information Science and Technology. It's my great honor to participate in today's ICCP Journal Club seminar. Today for our seminar, I'm going to be talking about the research during my PhD period. The topic is the influence of convective cloud entrainment processes and tenor drag on precipitation of the Tibetan Plateau. The research was mainly completed under the supervision of Professor Chun-Sung Lu and received the help from the persons listed here. At the beginning of this talk, I would like to introduce the research background of this study. The Tibetan Plateau is the third pole of the Earth. It has a strong impact on the weather in China through the atmospheric thermal pump and the water tower mechanisms. Clouds plays an important role in the atmospheric energy budget. The high terrain of the Tibetan Plateau allows the surface to receive stronger shortwave solar radiation, leading to an increase in surface sensible heat. Coupled with the abundant water vapor supply, it promotes the easier triggering of convective activities on the Tibetan Plateau and makes cloud and precipitation shows unique features. The unique features of cloud and precipitation cause precipitation simulation biases in the models. The Tibetan Plateau is one of the regions with the largest precipitation simulation biases in weather and climate models. In the past, this issue was often addressed by increasing the model resolution, mainly involving the resolution of convection and terrain in the model. However, even in a resolution of 2 km, the problems of overestimated precision and distribution biases still exist. Therefore, research on the physical skins in the model is needed. Some studies have evaluated the sensitivity of the precipitation simulation on the plateau to the cumular skin, microphysics skins, land surface skin, and boundary skins. The results show that the precipitation simulation on the plateau is most sensitive to the cumular skin. This may be because the summer precipitation on the plateau is mainly convective cloud precipitation, and the cumular skin directly determines the simulation of convective precipitation. At the same time, the cloud and precipitation process of the plateau has closely related to the unique terrain of this region. The rough terrain will affect the water vapor transport and the development of convection on the plateau. Therefore, to improve the precipitation simulation of the Tibetan Plateau, it is necessary to improve the cumular skin and the topographic skin in the model. The cumular skin is used in the model to characterize the convective activities in the subgrade and calculated convective precipitation. The entrainment rate the entrainment process plays an important role in the cumular skin. Entrainment refers to the process in which dry air entrains into the cloud from the environment. Therefore, the entrainment process makes the cloud mix with the environment, and it is an important process of the interaction between the cloud and the environment. The entrainment rate in the model is used to characterize the proportion of dry air entered from the environment into the cloud. Many studies have carried out on the entrainment rate. Researchers show that the entrainment rate is closely related to both the characteristics of convective clouds and environmental factors. Based on the characters of the entrainment rate and its relationship with various variables, many parameterization schemes for the entrainment rate have been established. For example, in some studies, the entrainment rate is regarded as a constant or a random distribution, while in others, parameters such as cloud height and environmental relative humidity are used to parameterize the entrainment rate. However, there is still no unified view on the parameterization of the entrainment rate. It is worth noting that the terrain of the Tibetan Plateau has a certain impact on the height of convective clouds, and there is also a certain connection between the entrainment rate and the cloud height. Therefore, the terrain of the Tibetan Plateau may affect the entrainment rate in this region, and the applicability of the previous entrainment rate schemes of the Tibetan Plateau need to be studied. The terrain is closely related to the cloud and precipitation process. Research shows that due to the obstruction of water vapor by the mountain, the precipitation on the southern slope of the Tibetan Plateau shows a steep-like distribution with the change of the terrain. Therefore, accurately describing the terrain is a precondition for accurately simulating water vapor transport and precipitation to characterize the impact of these terrains on the atmosphere. A topographic parameterization scheme is usually used in the model. The blue shading in the figure represents the actual terrain, and the gray shading represents the terrain in the model. When the horizontal grid spacing of the model is relatively close, the model cannot describe the real complex terrain. Wang et al. Improved the precipitation biases on the southern slope of the Tibetan Plateau by applying the topographic scheme. It should be noticed that although some studies have revealed the influence of the terrain of the Tibetan Plateau on water vapor transport and precipitation, the influence of the terrain of the Tibetan Plateau on the formulation of cloud and their features has not been fully clarified. Based on the above literature review, the problems of overestimated precipitation simulation and distribution biases over the Tibetan Plateau exist in various models. The precipitation simulation in this region is relatively sensitive to the cumulus scheme and the topographic scheme. To improve the precipitation simulation of the Tibetan Plateau, there are three issues that need to be analyzed. First, how to establish a parameterization of the entrainment rate considering the terrain of the Tibetan Plateau. Second, can the improvement of the parameterization of the entrainment rate improve the precipitation simulation of the Tibetan Plateau? Third, how does the topographic drag affect the physical process of cloud and precipitation of the Tibetan Plateau? To answer the first question, we calculated the entrainment rate of the Tibetan Plateau region using satellite data and reanalysis. The calculation of the entrainment rate is based on the conserved variable of more static energy. The right figure shows the calculation method of the entrainment rate. The blue dotted line in the figure represents the most static energy inside the cloud without the influence of entrainment, and the blue curve represents the most static energy inside the cloud under the influence of entrainment. HE denotes the environmental most static energy, and DZ represents the cloud depends. After expanding the formula, the DHC divided by DZ represents the vertical change rate of most static energy inside the cloud. The lambda on the right represents the entrainment rate. The HC minus HE represents the difference in most static energy between the inside and outside of the cloud. So the right side of the equation represents the impact of entrainment rate on the most static energy. After calculating the entrainment rate, we obtain the horizontal distribution of the entrainment rate of the Tibetan Plateau. The result shows that both the entrainment rate and the environmental relative humidity decrease with the increase of terrain height. Overall, these two variables show a positive correlation. To verify the relationship between them, we group the samples of convective cloud and calculate the correlation coefficient between entrainment rate and relative humidity in each group. The results show that as the terrain height increases, the correlation coefficient between the two changes from positive to negative. To find the reason for the change in the correlation between the two, we decomposed the formula for the entrainment rate. According to the theoretic expression, the correlation between the entrainment rate and the three terms should be positive, negative, and positive respectively. The results show that below a terrain height of 1 kilometer, the decisive factor of the entrainment rate is the difference in most static energy between the inside and outside cloud. In the range where the terrain height is larger than 1 kilometer, the decisive factor of the entrainment rate is the difference in most static energy between the cloud base and the cloud top. Therefore, we divided the correction coefficient into three groups. In region 1, the entrainment rate is positive correlated. and the decisive factors is the difference between the environment and cloud. This is in line with the previous theoretic understanding. That is, when the relative humidity increases, the environmental more static energy increases, and the difference in more static energy between the inside and outside of the cloud decrease. So the entrainment rate will increase. In the region 2 and 3, the decisive factors of the entrainment rate is difference in most static energy between the cloud base and the cloud top, but the relationship between entrainment rate and relative humidity are different. For region 2 and 3, we found that the position of the cloud base relative to the turning point of the environmental static energy plays a decisive role. In region 2, the cloud base is always below the turning point of the environmental static energy. When the relative humidity increases, the cloud base height decreases. At this time, the more static energy of the cloud base will increase. So the difference in more static energy between the cloud base and the cloud top will increase, and the entrainment rate will increase. In the region 3, the cloud base is about the turning point of the most static energy. When the relative humidity increases, the cloud base height also decreases, but the more static energy decreases. So the difference in more static energy between the cloud base decreases, and the entrainment decreases. Based on the relationship between the entrainment rate and the environmental relative humidity, we attempt to establish a parameterization scheme for the entrainment rate. The result shows that the determination confidence of the entrainment rate fitting formula using only one variable for environmental relative humidity is relatively low. The formula, including term factors, has a higher determination confidence, and the formulation scheme using the term cloud base height and environmental relative humidity has the highest determination confidence. Therefore, we take this scheme as a parameterization of the entrainment rate for Tibetan Plateau. After establishing the parameterization of the entrainment rate, we have answered the first question raised early. Next, I will attempt to couple the newly established entrainment rate parameterization into the Wolf model to answer the second question. To improve the cumulus gain, we use the Wolf model to conduct a one-month simulation of the eastern and southern part of the Tibetan Plateau. The cumulus gain we select is the GF scheme. This is the parameterization formula for the entrainment rate in GF scheme. The parameterization is mainly based on relative humidity. We denote the experiment using default GF scheme as a control, and the experiment uses the new entrainment rate parameterization as the SNPP. The two figures on the left show the total precipitation distribution of GPM and the control. The precipitation distribution in the control and GPM observations are generally similar. The two figures on the right show the difference in precipitation distributions between control and GPM, as well as between control and SNPP. The control significantly overestimates precipitation. The SNPP can reproduce the precipitation in most parts of the simulation areas, showing a significant improvement in precipitation simulation. The left figure shows the simulated precipitation time series. This is the result of the regional average. It can also be seen that the control overestimates precipitation for most of the time. The improvement effect of the SNPP or precipitation series is also obvious, making the curve of the precipitation series closer to the observed curve. The right figure shows the probability density distribution function of the simulated precipitation. Compared with the GPM, the control simulates a higher frequency of heavy precipitation and a lower frequency of weak precipitation. This is an important reason for the overestimation of precipitation in the control. The SNPP shifts the probability density distribution of precipitation towards the towards the lower value range, making the probability density distribution of precipitation closer to the observed values. Combined with the research content of the previous part, we can also verify the simulation effects through the distribution of the entrainment rate. Compared with the observed results, the entrainment rate in the control has a smaller value and shows a large deviation from the observation. The entrainment rate in the SNPP has a large value and its distribution is also closer to the observation. The above analysis shows that compared with the default scheme, the new scheme has certain improvements in both precipitation and entrainment rate. After verifying the reliability of the simulation results, we further analyze the mechanism by which the new scheme improves precipitation. These two figures are the probability density distribution function of cloud top height and cloud depends. Compared with control, the large entrainment rate in the SNPP suppresses the development height of convective clouds, reduces the cloud top height and cloud depends of convective clouds, and shifts the probability density distribution of cloud top height and cloud depends towards the lower value range. The left figure shows the vertical profile of proportion of cumulus grades in the model grades, and the right figure shows the difference in surface precipitation grades between control and SNPP. Compared with the control, the SNPP has a smaller proportion of cumulus grades in vertical loess and a smaller proportion of surface convective precipitation grades. This may be because the reduction in the cloud top height and the cloud depends make it possible for some convections that could have formed to occur, thereby reducing the proportion of updrafts in the lower loil. The reduction in the cloud top height and cloud depends also prevents the updrafts from developing to the upper loil, reducing the proportion of updrafts in the upper loil. The reduction in the proportion of updrafts in the vertical loil may also lead to a decrease in the precipitation that can be found in the column when the condensed rain is less than the evaporated rain. Convection cannot form, resulting in a decrease in the proportion of surface convective precipitation grades. In addition, the decrease in the convection that could have formed also leads to a decrease in the proportion of surface convective precipitation grades. These two figures are the probability density distribution functions of convective precipitation intensity and the cloud water path, respectively. Compared with the control, the SNPP has a smaller convective precipitation intensity and cloud water path. This indicates that the increased entrainment rate enhances the mixing between the cloud and the environment, and the evaporation at the lateral boundary reduces the water content in the cloud and thus weakens the convective precipitation intensity. So far, we have answered the second question. We have improved the precipitation simulation of the Tibetan Plateau by improving the entrainment rate parameterization. Next, we explore the influence mechanism of topographic drag on the physical process of cloud and precipitation of the Tibetan Plateau to answer the third question mentioned earlier. The simulation area we select is the foot and slope region in the southeast part of the Tibetan Plateau, and the simulation period is June and July 2019. We choose the topographic drag parameterization method as the topographic scheme and decide experiments with the topographic turn off and on, denoted as control and TFD. We first verify the simulation result. The left figure shows the total precipitation and root mean square error of 22 precipitation stations in the simulation area. Compared with the control, the total precipitation of the TFD is closer to the observed value at 70 stations, and the root mean square error of the TFD is smaller at 18 stations. It can also be seen from the total precipitation of all stations that the TFD significantly reduces the total precipitation, which is closer to the observed values. The right figure is the horizontal distribution of total precipitation. Compared with GPM, The control overestimates the precipitation on the slope and underestimates the precipitation on the foot. Compared with the control, the TFD reduced the precipitation on the slope and increased the precipitation on the foot, making the precipitation distribution closer to the observations. To reveal the mechanism by which the TFD adjusts the precipitation distribution, we first present the water vapor transport situation. TFD almost reduced the water vapor transport in the entire region. For the values of water vapor, more water vapor is reduced on the foot, which is inconstant with the increase in precipitation on the foot. Therefore, the weakening of water vapor transport in the TFD cannot fully explain the adjustment of precipitation in the TFD. Then we divided the research area into two regions, the foot and the slope. The TFD increased the proportion of heavy precipitation and decreased the proportion of light precipitation on the foot, while increasing the proportion of light precipitation and decreasing the proportion of heavy precipitation on the slope. Considering that the main effect of TFD is reflected in wind speed, the left figure shows the profiles of the wind speed. The TFD weakens the wind speed on the foot and on the slope. The right figure shows that the impact of the TFD on vertical velocity. The TFD enhances the convergence and the vertical upward motion on the foot and weakens the convergence and upward motion on the slope. To explain the reason why the TFD weakens the wind speed and then enhances the vertical velocity on the foot, the left figure shows the horizontal wind speed at 825 hectopascal. The effect of TFD weakens the horizontal wind speed on this level, reducing the climbing ability of these air flows and causing them to accumulate on the foot, thus enhancing the convergence and the vertical velocity on the foot. The increased vertical velocity on the foot further enhances the cloud microphysical processes, thus increasing the rainwater mixing ratio and surface precipitation. The decreased vertical velocity on the slope weakens the cloud microphysical process, reducing the rainwater mixing ratio and surface precipitation. We also explore the impact of TFD on precipitation on the different precipitation intensities. The blue shading in the figure represents the weak precipitation period, and the green shading represents the heavy precipitation period. Compared with the weak precipitation period, the impact of TFD on precipitation is greater during the heavy precipitation period. This is mainly because the wind speed is higher during the heavy precipitation period, and the impact of TFD on wind speed is also greater. As a result, it has a greater impact on vertical velocity, cloud microphysical process, and rainwater mixing ratios. Finally, we use the optimized convective entrainment rate scheme and the TFD scheme to explore whether they can jointly enhance the precipitation simulation. We choose the entire Tibetan Plateau for simulation. The simulation period was till June and July 2019. The 4 experiments were designed. Control used the default GF scheme with the TFD scheme turned off. SNPP only modified the commoner scheme. TFD only turned on the TFD scheme, and modified used the improved commoner scheme and turned on the TFD scheme. First, we present the horizontal distribution of precipitation. Like the previous conclusion, the control overestimates precipitation across the entire Tibetan Plateau. The 3 sensitivity experiment improved the precipitation on the Tibetan Plateau. The 2 experiments with optimized entrainment rates had the greatest impact on the precipitation amounts. The TFD experiment could reduce the precipitation in most areas of the Tibetan. It should be noticed that the SNPP increased precipitation on the southern slope of the Himalayas, deviating from the observed values. The addition of TFD in the modified could improve the overestimated precipitation in this region. The TFD scheme had a relatively small impact on the region precipitation time series and the precipitation probability density distribution, while SMPP and modified had better improvement effects on the precipitation time series and probability density distribution. Based on the above analysis, we can find that the improved cumulus gain weakens the simulation of total precipitation in the region. The TFD gain adjusts the distribution of precipitation simulation in the region. And the TFD gain could make up for the shortage of the improved cumulus gain in the precipitation simulation on the southern slope of the plateau, making the average precipitation in the modified closer to the observation, and the IMS is the smallest. Next, we will separately discuss the improvement mechanism of the improved cumulus gain on the overall precipitation in the region, and the improvement mechanism of the TFD gain on the precipitation on the southern slope of the Himalayas. First is the cumulus gain. The main idea is like the previous part. From the vertical profile of the entrainment rate, we can see that the optimized cumulus gain increases the entrainment rate. The increased entrainment rate reduces the number of updraft grades, cloud depends, cloud water content, and the convective precipitation intensity, and ultimately reducing the total precipitation. Then is the TFD gain. We conduct a regional average of the southern slope of the Himalayas. The impact mechanism of the TFD gain on the precipitation in this region is also like that machine before. The TFD gain reduces the low-level wind speed in the region, and thereby reducing the vertical velocity precipitation particles in the cumulus schemes and precipitation particles in the microphysical schemes. The main conclusions are as follows. First, a parameterization scheme of the convective entrainment rate considering the terrain of the Tibetan Plateau has been established. Second, the convective scheme is improved to address the overestimation issue in the precipitation simulation of the Tibetan Plateau. In addition, the mechanisms of the terrain scheme on the simulation of clouds and precipitation under different topographic conditions is elaborated. Finally, through the joint use of the improved cumulus scheme and the topographic scheme, we enhance the accuracy of precipitation simulation on the Tibetan Plateau. This is all for my report. Here are some relevant papers. Thank you.
Thanks a lot, Jin, for your interesting talk. And